integration topic. We're still doing some prerequisites, things which hopefully you've come across before, but it's worth just reminding you of all these basic skills. It's the one kind of topic that you really need to be on top of these things. We're talking about the area bounded by a line and a curve. So we're going to use some of the fundamental theorem of algebra here. There's no picture tragedy, so we'll maybe think about that. Drawing a sketch might help about getting an idea of our bearings here. Calculate the area bounded by the line y equals x plus 2. That's a line with a positive gradient of 1, cuts at y, intersect at 2. So it's going to be something like that. A straight line. Y equals x plus 2. And a curve y equals x squared, which of course is just a parabola with a turning point on the origin. Something like that. Y equals x squared. So we're talking about the area which lies between these 2 points, these 2 curves rather. So we need 2 points of intersection. We need this point here, A, and we need this point here, B. Our left and right, our upper and lower bounds to know how to use our integration. So we need to find those points of intersection. And we find the points of intersection because at those points, the x value, or we usually do it in the y value of the curve is equal to the y value of the line. In other words, we can just make the 2 equations equal to each other. So if we're saying the y terms have to be the same at those points, then we can say therefore that x squared is equal to x plus 2. If we're equating the left-hand side, we can also say that the right-hand sides are equal, which means that we can rearrange that, subtract x from both sides, subtract 2 from both sides, and we end up with our quadratic equation, which we can factorize, hopefully. Factors of -2, which add to -1, -2, and +1, which means that either x minus 2 equals 0 or x plus 1 equals 0, and our solutions are x equals 2 and x equals -1. What does that mean? It means that a here is -1 and b here is 2. That's our upper and lower bounds of the integration. So we're then wanting to find the area between the line and the curve. For this particular situation, the upper function is the line and the lower function is the curve. So we can say that the area between the curve and the line is equal to the integral from -1 to 2 of our upper function, which is the line, x plus 2, minus the lower function, which in this case is x squared. We can't really simplify that because there's no like terms, so we can in a way just go around integrating it. So we can integrate x to x squared over 2 plus 2x minus x cubed over 3 from 2 to -1. Substitute in. We've got 2 squared. I'm just going to do this quickly without writing it all out. So 2 squared is 4, divided by 2 is 2, plus 2 times 2 is 4, minus 2 cubed is 8 over 3. So that's what we get from the first substitution. Second one is -1. -1 squared is 1, so my first term is a half. Second term becomes -2. And my third term, -1 cubed, is still -1, so it becomes plus a third. And just tidying all of that up, simplifying it. On the we could actually just deal with the whole numbers first. So we've got 2, add 4 is 6, subtract -2 gives me 8. we've got negative 8 thirds, and then later on subtract another 1 third, which is negative 9 thirds, which is negative 3, and then we've still got minus a half. So it's 5 subtract a half, which is 4.5. 4.5 what? 4.5 square units, because we're actually talking about the area, is 4.5 square units between the line and the curve. Okay, you might have a different way of working out that last section. There's various ways to evaluate it, but that was one of the ways. Okay, hope that makes sense.